Okay, so in this lecture, we are going to give a brief introduction about the phenomena of polarization. The first thing you have to remember is the polarization is a phenomena related to wave. Okay, so it is a phenomena related to wave. Okay, so I think all of you already aware about what is meant by a wave. So I am not going to stress on it. So the wave we can classify into two categories depending upon the way of vibration and the way of oscillation in the wave. Okay, the one type is called transverse wave, and the other type is called longitudinal wave. So however the phenomena of polarization is applicable only for transverse wave. So what is in a transverse wave? So what's a transverse wave? So transverse wave are the waves in which the oscillation of the particle is perpendicular to direction of propagation. So better instead of talking all this theory, we can have simple examples to understand the difference between the transverse wave and longitudinal wave. So the very good example is, so consider a string. Okay, I think instead of string we can have a spring. That would be better because we can discuss both type of oscillation using one example. That would be better. So consider a spring. Which is attached to one end, another end is free. Now let us suppose you have started vibrating the free end up and down. Okay, suppose you have started vibrating the free end like this, the up and down. What would happen? There as oscillation will set up on this spring, and the oscillation would be along this direction, up and down direction. However, there would be the propagation of oscillation towards right. So there will be energy transfer towards right. The energy will propagate towards right, but all the particles or all the uh, spring, each and every point of the spring will go just up and down. So each and every point of the spring will just go up and down, and the energy will propagate forward. So this kind of propagation of energy, or this kind of wave, is called a transverse wave. So if you look at it very carefully, the shape of the spring would be like this. If we start oscillating it, okay, so we can just put some curl here. Okay, so after a later time, the there will be a wave would be set up in this spring, and we'll get this kind of shape. And you already know the different uh, aspects of this wave and all. So I'm not going to discuss about it. The different parts, the crest, trough, etc., wavelength. So all these aspects you already know it. So I am not going to discuss into that. And for that you will learn it through some other chapters. Okay. So I am very bothered about the phenomena of polarization. So that is why I'm not going to very deep into the concept of wave and all. So those of you, if you are interested, just to go and refer your higher secondary textbook, you get the basic idea about the wave and all. Okay. Now, so this is an example of transverse wave. So here all the the spring particles are just going up and down. The spring particles, if you look at, it will just going up and down, but the energy is going forward direction. Now there is another type of wave called longitudinal wave. So in case of longitudinal wave, right here, longitudinal. Again, we can take a same example. The example that I have taken is a spring. It is attached to a fixed wall. The one end is attached to a fixed wall. The other end is free. Now again, we are going to set up a vibration here, an oscillation here. But now I am going to set up the oscillation in the horizontal direction. So I have started oscillating the free end in this direction. Then what would happen? The spring will it look like this? No. What would happen? The each and every point of the spring will move like this, and the energy will go forward. The energy of the oscillation that will move forward, but the spring particle will move the backward and forward direction. Okay, so then instead of happening the crest and trough, here we'll get the compression region or rarefaction region. So what would happen is, at some point in time, if you take a photograph of this spring, what would happen is you can see that at some point the spring would be very close to each other. At some other point, the spring particle will be very far from each other. So I will just draw the figure. Okay, suppose this point, the spring particle are very close. This kind of way. So here you can see, if you look at this position, the spring particle are very close. At this region, the spring particle are very far away from it. Okay, so these regions are called the compression region, rarefaction region. And when time move forward, accordingly, the position of the compression rarefaction would also change. Okay, so this is very easy to demonstrate. If you have a very long spring, you can easily demonstrate this kind of the different types of wave, the transverse wave and longitudinal wave. So in case of transverse wave, the basic idea is, in case of transverse wave, the oscillation of the particle is perpendicular to the propagation of energy or the propagation of wave. So this is the propagation of energy or the propagation of direction of propagation of wave. And in case of longitudinal wave, the direction of oscillation is parallel to the propagation of energy or wave. Okay, so direction of propagation of wave is same as the direction of propagation of energy. So that is the key point you have to understand. So I will write down here. So transverse wave, here a particle oscillation is perpendicular to direction of propagation of wave. The direction of propagation of wave is same as energy. And in case of longitudinal wave, particle oscillation is parallel to direction of propagation of wave. So that is the takeaway of this section. Okay, now in case of transverse wave, we have a choice for oscillation. But in case of longitudinal wave, there is no such choices. The thing is, if you look at the transverse wave, I already said in case of transverse wave, the oscillation of the particle must be perpendicular to the direction of propagation. So if, okay, so better what I can do is I can assign some direction. Okay, I'm assigning towards right as X and upward I will denote as Y, and towards you I will denote as Z. Okay, so there is a usual Cartesian coordinate system, direction X, Y, and Z. Okay, now suppose X is the direction of propagation. So if X is the direction of propagation, then in case of transverse wave, there are two independent directions for oscillation. It can, the wave, the particle can either oscillate along y direction. It can either oscillate along y direction, as we have seen in this example. See, in this example, the particles are oscillating along y direction. That is possible. And what is the other option? Can you think about it? The other option is it can oscillate along z direction. So both these directions, the y direction and z direction, are exactly perpendicular to the x direction. So y and z are perpendicular to x. So there are two independent directions for oscillation. So that means we have infinite possible choice for the direction of oscillation in case of a transverse wave. So here I have just shown only two, but it can oscillate along this direction as well. Okay, so this is in the zy plane. You have to view in that. Okay, it can be in some diagonal direction in the zy plane. It need not be exactly along y. It need not be exactly along z. It can be in the diagonal also. Okay, so it can be some inclined direction as well. So this is one possibility, or there would be infinite possibility for the oscillation, the direction of oscillation for the transverse wave in the case of transverse wave. But what about longitudinal wave? In case of longitudinal wave, the oscillation should be strictly along the direction of propagation of wave. So there is no choice for us. Okay, but in case of transverse wave, there is a choice for the direction of oscillation. So here comes the importance of polarization. So what is a polarization? Okay, now I already said that in case of transverse wave, there is infinite possible choice for the direction of oscillation. But if you fix, or if you can able to fix the direction of oscillation along one direction for a transverse wave, then that wave is called a polarized wave. Or in other words, the polarization is a phenomena to fix the direction of oscillation of a wave in along one direction. അപ്പം നിങ്ങൾക്ക് ട്രാൻസ്വേഴ്സ് വേവിന്റെ ഓസിലേഷൻ ഒരു നിശ്ചിത ഡയറക്ഷനിലേക്ക് നിങ്ങൾക്ക് കൺഫൈൻ ചെയ്യാൻ പറ്റുമെങ്കിൽ that phenomena is called the polarization, and that wave is called a polarized wave. Okay, so remember, in case of transverse wave, there are infinite choices available for oscillation oscillation of particle. Now, if we fix the direction of oscillation, then the wave is called transverse oscillation. The wave is called polarized wave. Okay, so we can have some more explanation in the next slide. Polarization. So better we can take a similar example. So consider a spring. Okay, now no need to look into the longitudinal wave for the time being, because we have to focus our entire attention to the transverse wave, because the polarization phenomena is possible only for transverse wave. Okay, but longitudinal wave, there is no choice. The oscillation is always along one particular direction, so there is no choice for longitudinal wave. So there is no point of on discussing the possibility of polarization on longitudinal wave. But whereas in case of a transverse wave, there is a choice for the oscillation of wave, and hence we have to define, or we can indulge the phenomena of polarization for, or we can discuss the phenomena of polarization for a transverse wave. So better consider a string. Consider a string. Again, we can have it is fixed at one end. Okay, if it is not fixed also, there is no issue. And you have started oscillating the free end, but you are not oscillating the free end in one specific direction. If you're oscillating the free end in all possible direction, which is perpendicular to the string, then what would happen? There may be many possible type of oscillation would come here. You can get this kind of oscillation. We may get this type of oscillation, or we may get this type of oscillation. So there will be many different types of oscillation would come here, and it would be completely fuzzy. So this kind of wave we call unpolarized wave. So it is a transverse wave. Okay, so first of all, it's a transverse wave, but the direction of oscillation of wave is not fixed. It is randomly oscillating in all possible directions. It's oscillating in vertical direction, horizontal, and inclined direction. In all directions, it is oscillating, because you are randomly oscillating the free end. You are not oscillating along one particular direction. You are randomly oscillating the free end. Okay, so this kind of wave I can call it as an unpolarized wave. Now it is possible to convert this unpolarized wave into a polarized wave, and that is very simple to do in case of a string. So what you have to do is, okay, so just remove this wall, and let us assume the string is more lengthy. Okay, and the wall is here. Okay, so what I can do is I can put an arrangement here. So the arrangement I will be putting here, it is just a slit. So consider a slit which is a very narrow opening in the vertical direction. All these are closed. So it is a very narrow opening along the vertical direction. So what would happen? This slit, so it is a slit, vertical slit. So this vertical slit will permit only vertical oscillation to pass through it. It will block all other oscillation. It will block horizontal oscillation and inclined oscillation, but it will accept, or it will transmit the vertical part of inclined oscillation, because we know that suppose the wave is coming towards you, and the oscillation of wave is like this, inclined, and your slit is vertical. Slit is vertical. Then you can resolve this oscillation, this inclined oscillation, into two category: a horizontal oscillation and a vertical oscillation. Okay, so this kind of resolution you already know. Suppose this angle is theta, and the incident amplitude is A, then this would be A cos theta. The horizontal would be, sorry, vertical would be A cos theta, and horizontal would be A sin theta. Okay, so this is just a simple resolution of vectors. Okay, so anyhow, what would happen is the vertical slit will pass only the vertical oscillations, and all other oscillation will be stopped. So then after this vertical slit, what would be the shape of the wave? So that would be exactly vertical. The string will oscillate exactly along the vertical direction. There is no the oscillation in other directions. So here I have fixed the direction of oscillation into one plane. Okay, in earlier, in the case of unpolarized wave, the direction of oscillation is completely random, and here it has some order. It is oscillating along one particular direction. So this is an example for a polarized wave. Okay, now the device which converted the unpolarized wave into a polarized wave, technically it is called a polarizer. Okay, so here since it is a mechanical wave, the wave which is produced in a string is a mechanical wave, so I can use this kind of vertical slit arrangement to polarize it. So depending upon the wave, the type of polarizer would also change. Okay, the polarizer is not always the vertical slit cannot be used for all type of wave. Suppose if you are using light, obviously this kind of slit cannot be used as a polarizer. So for a wave which is propagating on a string, can be polarized using a vertical slit, and here the vertical slit uh, plays the role of a polarizer. Okay, so then the question is, we have a different question: what is a polarized wave? So I have answered it now. What is an unpolarized wave, and what is a polarized wave, and what is a polarizer? So I have answered for the three questions here. Okay, so if somebody asked to you, that is what is an unpolarized wave, then you can easily say that the unpolarized wave or the transverse wave in which the direction of oscillation are completely random. Okay, and what is a polarized wave? The polarized wave or the transverse wave in which the direction of oscillation is confined onto one plane. So if the direction of oscillation is confined on a plane, on a single plane, then we call that wave is a polarized wave. And what is a polarizer? The polarizer is a device which converts an unpolarized wave into a polarized wave. So this is what is maybe polarization. This phenomena is basically what is called the polarization. So the polarization phenomena is applicable only for transverse wave. Okay, so polarization is applicable only for transverse wave. So why it is so? So that also I have answered, because only for the transverse wave we have a choice. We have different choice for oscillation. Then only the question of confining of oscillation will come. Otherwise, in case of longitudinal oscillation, there is no choice. It has to be, the direction of oscillation has to be along the direction of propagation. There is no choice for the direction of oscillation in case of longitudinal wave. But for the transverse wave, there is a choice. Okay, so we can have, at a time we can have different direction of oscillation for a transverse wave, and you can, it is possible to fix the direction of oscillation through a polarizer. So the phenomena of the polarization is applicable, or it is possible only for transverse wave, and its basic idea I have just illustrated in this figure. And it is very easy to demonstrate all these things in your class. Just you want to have a very long string and a vertical slit, you can just show it. Okay, you can carefully you can design and demonstration and perform this experiment to demonstrate what is meant by a polarization, or what is, how to convert an unpolarized wave into a polarized wave. Okay, so for the time being we are stopping it here. So but so till now what we have discussed is what is the polarization of a wave in general, but we have to discuss the polarization of light. So in the next class I will come here to discuss what is meant by the polarization of light.